Hey everyone, Mr. Skelton here. We are back at it to begin Unit 8. This is Lesson 1 on functions, and our function unit is pretty short and sweet. This first lesson is, honestly, it's all review from Algebra 1. I put a couple notes down on the front slide here about functions, and we're going to expand on that more as we get into this unit. But basic stuff from Algebra 1 is a function is something where you can plug an x into a function, an equation, and it generates an output. Your input is your x values, your output your y values, your function is the equation you plug it into. And there's a general rule for function, and then that is 1 to 1, meaning that for every input there's exactly one output for it. In today's lesson, we're going to be focusing on some of the graphs, and so a lot of this is review. You'll see on your first slide as we move to it, where you're just graphing a linear function. This would be a linear function, and we want to graph this. So it's just kind of some review of the rules of graphing types of functions. So if you can do this on your own, go ahead and hit pause and do that. Here's our y-intercept, right? This is y equals mx plus b. So -4 would be our y-intercept. That's where we would start. We would leave our pen or pencil on that y-intercept and apply our slope. Our slope would be the 2/3. So we're going to go up 2, 1, 2, and to the right 3, 1, 2, 3. And we could continue that up to 1, 2, 3, over and over and over again. We can also go down 2 and to the left 3 as well. And we can connect our dots and draw a straight line. Okay, slope is consistent, and that's why you get a nice line, because you just continue to apply the slope over and over again. All right? This is a linear function as well, but you'll notice that this is in standard form. Call standard form, and you can change this. You have options here. You can change this to y equals mx plus b if you would like and graph it. Or standard form, what is standard form used for? It's to find the x and y intercepts. In other words, where the graph crosses the x and y axis. And so with standard form, what we do is we will plug in a 0 for x and solve for y, and we will plug a 0 in for y and solve for x. Back in algebra, I used to call it the cover-up method, right? So when you notice that x and y are on the same side, that's standard form, if you cover up the x just with your finger, which means I'm plugging in a 0 for x, that's the reason I'm covering it up, is because 3 times 0 would be 0, and then I can just solve that for y, so I'd get -3. Likewise, I can cover up the 4y, if I can do that, and you get 3x equals 12, which would just give me 4. So this would be 0, -3, and 4, 0. And when you draw the line between those, there's your function, there's the graph of your function, and you can see that your x-intercept is 4, 0, and your y-intercept on the y-axis is 0, -3. That's your y-intercept, and that's your x-intercept. And that's what standard form allows you to do. Again, you could change that to y equals mx plus b and solve for y, and you'd get the same exact thing. Okay? Moving on. So you've done this is a parabola, this is a quadratic, right? Quadratic function. And so a lot of the times with quadratic functions, most students already know the general shape. You're either going to have a smiley face, right, or a frowny face. And the only time you would have that frowny face is if your function was negative, right? If your a value was negative. So we can just pick some points here, make a t-chart. That's usually the most common thing, 0. If we plug in a 0, we get 0 back, so 0, 0. 1 would be 1, -1 would still be 1. We can go 2, and we'd get 4, and we can go -2, and we'd still get 4. So 1, 1, okay, and 2, and 4, and -2, and 4. And there's our parabola right there. All right, and you can pick more points if you'd like, but there's your parabola. We would refer to this, we would refer to this as the parent function. And because that's the most basic quadratic you can get, and then what we have done in the past is we have made some adjustments to this, which we've slid it left to the right, we've moved it up and down, we've stretched it, we've shrunk it depending on the a value, and we're going to get into some of that here in a little bit. On the back side, absolute value, we did some of this, I believe, in the first semester. So absolute value, the way to remember what does this look like, absolute value with a v. The absolute value graph is a v. Again, you can make a t-chart on this. Again, this would be the parent function, the most basic absolute value function that we have. And again, 0, 0 would work. and we can go 1 and 1, negative 1 and 1, 2 and 2, etc., etc. So 1, 1, 1, 1, 2, 2, 2, 2, and we're making a V here. And there's your absolute value function graph. Okay? Those were the basic functions that we've covered before, and here is our transformations. Transformations are basically your movement. Okay? Up, down, left, right, stretch, and shrink. Okay? Those are the three that we usually cover when we're doing these functions, when we're graphing them. So you can see here I've listed the parent function, we already talked about that, and then our changes. And we've discussed this, so this should be review for you. With the linear function, it's the same thing. You'll notice there's no exponent here. With the h and the k, you also have the h and the k for the quadratic, the h and the k for the absolute value, and we're going to talk about those shifts here again in a minute. All right, so let's turn the page here. So most of you, again, what you want to be able to do is ask yourself, how is this changed from the parent function? Okay, and if you need to, if you need to go back to the parent function of y equals absolute value of x, just to show you here, to prove to you 0, 0, I'll graph this in red, 1, 1, negative 1, and 1. Okay, 2 and 2, negative 2 and 2. Remember, I'm taking the absolute value, that's why I'm getting positive 2 here. So there's the parent function. So if I go and graph now this absolute value equation, I want to zero this out, meaning I want to make whatever's on the inside 0. So what would it take to make the inside of the absolute value bars 0? So before I take the absolute value of x, I need to subtract 2 from that. So I would pick a 2 to make that a 0. So at 2, 0, there's my point. Now if I pick like the number 3, 3 minus 2 would give me a 1. Okay? So here, if I picked positive 1, I'm picking points from to the left and to the right of what the vertex is going to be. And then I can pick a 1, and I would still get 1, because I would have 1 minus 2, which is negative 1. The absolute value of negative 1 is 1. And so what happened to every point on this blue graph compared to the parent function? Everything slid to the right two spots. Okay? And so that's our anything inside the absolute value bars, the parentheses. We always think of it, you can think of it as the opposite of what the sign is. This is the negative 2, so you're going to slide everything to the right 2. Okay? Here's another example. Again, the parent function would just be y equals x squared, and we've done this before. Again, review-wise, you could graph this very quickly. That's just a really rough sketch. But if you made a t-chart again for the parent function itself, okay, and we want to zero this out, we would plug in a negative 3, right? Negative 3 with negative 3 plus 3 would be 0. 0 squared would be 0, so have something like this. And we could pick points like negative 2. Negative 2 plus 3 would be 1. 1 squared would be 1, so negative 2, 1. And negative 4 would be negative 1 squared, which would be 1. And you can see my graph in red of the parent function. So what did every point from the parent function do when we applied this plus 3? It slid everything to the left 3 units. Okay? And so anything, it says adding or subtracting a number before squaring or taking the absolute value represents a horizontal shift. Again, everything was shifted to the left 3 units. Okay? So a quick review on any time we have a k value, this is your k value here. Go ahead and hit pause and try this one here on your own. So the parent function again would be y equals just x squared, which would just be this in red, kind of going against my colors here. If I graph this one in blue, plus 2, and make a t-chart, if I pick a 0 for x, I square it, get 0 plus 2 would be 0, 2. So there's my graph. If I pick like a 1, that would be 3, so 1 and 3. If I pick negative 1, I'd still get 3. And you can see my parabola in blue, which is this function here. What happened to every single point on the red to the blue? It moved up 2 units. Okay, and so anytime you have a k value, which is the number outside of the parentheses or absolute value bars, there is a vertical movement either up or down, and it's true to the sign. So if you have plus 2, you're moving up. If this is x squared minus 5, you'd move it down 5. Okay. This one is often very much comes into question with students when you have an a value. This is the a value, and it's out front. Well, what does the a value do? Well, if your a value is positive, that means you're going to have an absolute value. Since this is absolute value, that would open up. If your a value is negative, you're going to have an absolute value that would go down, right? Same thing with quadratics. You have a smiley face or a frowny face based on your a value. And then, excuse me, the number itself. So let's graph the parent function. So the parent function would just be the absolute value of x, which is just going to be something like this: 0, 0, 1, 1, negative 1, 1. We'll do this very quickly, and we already know because we've already graphed it. There's the parent function. Okay. Let's take a look at a t-chart with this function right here, where we have the absolute, where we take the absolute value of x and then multiply it by negative 3. So if I have 0, I'm still going to get 0. Okay. If I have 1, absolute value of 1 is 1, and then negative 3. And then if I have a negative 1, absolute value of negative 1 is still 1, it would be negative 3. So 1, negative 3, and negative 1, negative 3. That would get something like this. I didn't pick a ton of points here. But basically your output is going to be multiplied by negative 3. All right? And so because this was negative, it flipped it upside down. Because this a value, the absolute value of the a value, is larger than 1, that's going to give you a stretch. Okay? It's going to give you a stretch because it's going to make it real skinny. A stretch is skinny. If your a value, if the absolute value of your a value is less than 1, okay, not less than or equal to, less than 1, that's going to be a shrink, where it gets really wide. Okay? And we've covered that before. This last slide here is basically just a list of all the transformations that we've covered already. This is a great slide to reference when you're studying in terms of your h and k and what it does. Your h value here translates it to the right and to the left, and it's always the opposite of what it is in the function. Your k value, which is outside, usually is going to move it up or down, and that's true to the sign, whether it's positive or negative. And your a stretches or shrinks the graph, stretches the graph, either stretches it vertically or shrinks it horizontally, and then it can also reflect if you have a negative a value. Okay. So this last one here, what we want to do is graph this, and the first thing we want to do is to be able to find the vertex. So where is the vertex? That's our h and our k, and so this is negative 3 and negative 1. So I'd go to the left 3 and down 1. My a value is positive. It's a positive 2. Since it's greater than 1, which means it's going to open up. Okay, so it's going to open up. Sometimes you can make little notes to the side. It's going to open up. It's going to be a v because it's absolute value. And because it's multiplied by 2, that means it's going to get skinny. It's going to stretch. All right. And so what we can do is you can just make a t-chart if you would like. And we already know the vertex is negative 3, negative 1, so we can pick some points to the right or to the left, x values to the right or to the left of this. So, for example, negative 2. So if I plug in negative 2 for x, negative 2 plus 3 is 1. 1 times 2 is 2. 2 minus 1 is 1. So negative 2 and 1 would be right here. I could pick a point to the left, which is negative 4. Negative 4 plus 3 is negative 1. The absolute value of negative 1 is 1. 1 times 2 is 2. Minus 1 is 1. So negative 4 and 1 here. And this is, anytime you have an absolute value graph, it's going to be symmetric. And there's our graph there. Okay? And you can pick more points if you would like. Okay? So that lesson, I know 99% of it is all review, but it's good to go over because towards the end of this unit, we're going to be finding the inverses of all of these functions, and so I wanted to make sure we reviewed them and make sure you were good with linears, quadratics, and absolute value functions and graphing. All right? Look forward to seeing you in class. Take care.